and welcome back. This video is for our dynamic programming solution to the transitive closure problem. So the name of our dynamic programming approach is Warshall's algorithm. The problem is to get the transitive closure given an adjacency matrix of a directed graph. So on the left side, we can see the directed graph and its corresponding adjacency matrix. Okay, so note that the adjacency matrix here is not a symmetrical matrix. Okay, so since this is a directed graph, the corresponding transitive closure graph of this graph is a supergraph where it contains additional edges. So we know we have an edge connecting 2 to 3 because there is a path going from 2 to 3 in the original graph. So the transitive closure of a graph indicates whether there is a non-trivial path from I to J. So let's look at the adjacency matrix. Okay? So meron lang tayong mga new previously 0 items na naging 1 na because of the property that there is a non-trivial path from I to J. So to solve this problem using the dynamic programming, we can use the Warshall's algorithm. But before we describe, let us present the recursive relation. So, yes, the definition of a smaller instance here is that we only consider the vertices 1 to k na pwedeng daanan instead of all vertices 1 to n. So, this notation is actually an element of the matrix in the kth iteration. So, yung Warshall's algorithm actually is an iterative algorithm na ang dami ng iteration is n plus 1. So, this is the kth iteration. So, this value is 1 if sa previous iteration, the value is 1. Or this one. Okay, so this has a graphical representation. There is a path from I to J if there's a path from I to K and there's a path from K to J. So, ito lang basically yung gusto niyang sabihin. Okay, so kaya siya tinawag na transitive closure. It's because it's transitivity. So, parang, if there's a path from I to K and there's a path from K to J, then there's a path from I to J. At the iterative algorithm, we always start with the base case. And the initial case here, or the base case, is if we do not consider any intermediary vertex. So, if walang pwedeng madaanan, then we can only use direct edges between vertices. So we already have the adjacency matrix for that. Let's try to observe how the adjacency matrix evolves from the adjacency matrix, which is R0 to R4. So R4 is the target transitive closure graph of the given graph. So for R1, we are allowing vertex 1 as an intermediary node. That is why we have an additional edge 2 to 3 because there is 2 to 1 and 1 to 3 in the previous iteration. And if 1 na siya in the previous iteration based from rule 1, hindi na pwedeng mag-flip back to 0. Instead, yung mga zeros na lang in the previous iteration yung pwede nating i-flip to 1. Okay? So we need to check whether magwa-1 ba siya by allowing it to have intermediary vertex 1, intermediary vertex 1 and 2, and so on. Okay? So, in this case, we can see na nagkaroon na siya ng 3 additional because we allowed 2 as an intermediary vertex. And so on. Okay? So, just to formalize the rules, we have this and this to be the paragraph form of the recursive relation. The rule 1 is this one. If an element in row ij is 1 in the previous iteration, it remains 1. But if the element in the previous iteration is 0, it has to be changed to 1 if and only if yung elements nito and nito is also 1. Okay? In the previous iteration. So, let's try to do it in our example. So, R0 is the original adjacency matrix. We highlight columns 1 and row 1 because this will be the important elements for identifying if we can replace the zeros with a 1. So as you can see, may mga 1 na rin dito sa previous iteration. And in the next iteration, 1 pa rin sila. That's rule 1. And then, for the second rule, magiging 1 sa 0 if 1 yung 1 yung nasa ano bang tawag doon? Nasa IK and KJ. So, in this case, ito yung elements na yon. So, titingnan lang natin kung nasaan yung mga nag-1 and then yung element na to will be flipped to 1 because 1 ito and 1 ito. So, in the next iteration, you can see that there is an additional edge. And is changed from 0 to 1. In the next iteration, we highlight the second column and the second row because we are now allowing vertex 2 to be an intermediary node. So, in this case, we are interested in flipping the items na hindi highlighted. So, as you can see, we can flip this 1 to 1, this to 1, and this to 1. So, in the next iteration, we already have 3 additional edges for this R. So, R2. And then, for R2, we highlight the third column and the third row and see whether we can flip other items to 1 from 0. So, since we have an interesting case wherein our row here contains all 0 elements, hindi magiging 1 kapag nag-AND tayo. So, as you can see, sa next iteration, walang changes because 0 lahat ng mga nandito. Okay? So, walang new edge. Okay? So, the last column and the last row is highlighted for R3. Here, we can still flip some few. Based from the definition, we are interested with a 1 here and another 1 here. So, if 0 to, this can become 1 in the next iteration. So, for R4, this is the final graph. And this is the transitive closure of this graph. Okay, so this is the corresponding algorithm for what we did a while ago. This outer for loop is for the iterations from R0 to R4, and the inner for loop is for checking the contents of the matrix, whether we can put or whether we can flip the element from 0 to 1. Okay, so if it's 1, then 1 lang din. If it's 0, then dapat tama yung condition na to. For the time efficiency, since this is a nested for loop na tatlo yung levels, we have n cube. So that's for the time efficiency. And for the space efficiency, we have the container, which is the adjacency matrix na n squared. Okay? N squared because we can simply use the same matrix just by replacing some parts of it. Pero if you wanted to be safe, of course, you can maintain 2 matrices, one for the previous and one for the next iteration. Ayun. So, yun lang yung sa Warshaw's algorithm for the transitive closure.